Okay, everyone, welcome to class 19 of Physics 350. This is on Ohm's Law and motional EMF. In this class, we'll be looking at Ohm's Law, which has to do with how electric fields affect the flow of charge in materials, that is, currents. And we'll also be looking at we'll define EMF, electromotive force, and we'll be looking at motional EMF, which occurs when circuits move through magnetic fields. And the circuits moving through magnetic fields will be our first look at the relation between electricity and magnetism leading toward the Maxwell's equations in the next few classes. Okay, so Ohm's Law, you're probably familiar with Ohm's Law, but it's going to be presented in a slightly different form here. It's going to be written as J, the current density, is equal to sigma, the conductivity, times F. Now here F is the force per unit charge that's being exerted on electrical charges. And what this says is that the bigger the force per charge we put on, the bigger, the more charge density, charge flow we get. So if we double the force per charge, we double the rate the charge flows through a material. And the coefficient of proportionality is sigma, the conductivity. Now, we know what the force per charge is by the Lorentz force law, which is F equals QE plus QV cross P. If we divide that by Q, we get the force per charge. So it's just E plus V cross P. So we can replace little f here, the force per charge, by E plus V cross P. And then normally the velocity of charges cross the field. Typical field strength and typical velocities are small compared to typical electric fields. So generally we approximate this with just the current density is equal to the conductivity times the electric field. In plasmas, actually, this second term becomes important, since plasmas are ionized gases such as exist in the sun at very high temperatures. Anyway, this is Ohm's law. It may not be the form that you're familiar thinking of Ohm's law, which is probably V equals IR. So let's see how we can get from this J equals sigma E to V equals IR. So suppose we have a wire here with a cross-sectional area A and length L, and we apply an electric field to the left here, which will cause electrons to flow to the right. So we'll get, we'll have a current of electrons moving to the right, and the current will be moving from right to left. So the size of the current will be equal to the current density, which is the current per area, times the cross-sectional area. And then we can replace, according to Ohm's law, we can replace the current density, J, with sigma times E, because the current density is proportional to the applied electric field. And then finally, we can replace the electric field with the voltage difference between the two sides divided by the length L. And that's because the voltage is the magnitude of the voltage, that is equal to the electric field times the length for constant electric fields. Okay, so we've got the current is equal to sigma A over L, which are all constants, times V. So we have current proportional to voltage, which is what you normally associate Ohm's law as being. So we can say V is equal to IR, where here in this expression, I guess R would be, if we isolate V, we would have L over sigma A times I. So R would be L over sigma times A. Okay, but this is the fundamental kind of physicists think of this as the fundamental form of Ohm's law, and this is Ohm's law as applied to a wire. But this could apply to other types of materials, gases with charged particles in it or something. So this is the more fundamental expression. So why do we believe that Ohm's law holds? So if we think about a wire, if we apply an electric field to an electron, it's going to, remember that the wire is made up of a ton of atoms in a lattice. So the electron is going to bang around, colliding off atoms in the lattice, kind of like a pinball in a pinball machine. And we can define the typical time between these collisions that are occurring as the typical distance between atoms divided by, sorry, not the distance between atoms, but the distance between that occurs, the average distance between collisions, which is called the mean free path. That's the mean free path over the velocity associated with the thermal motion of the electrons. Okay, because we know that electrons move thermally. At a normal temperature, they're vibrating. Okay, so the typical time between collisions would be the mean free path over the thermal velocity. So then the average velocity would be equal to the average drift velocity, that is, moving to the right, would be equal to 1/2 times the acceleration times this average velocity between collisions, because right after a collision, the velocity is random, and so averages to 0. And after a time t, it's changed by the acceleration times this time t. So 0 plus at averaged would be 1/2 at. And then we can plug in t here, and we get a lambda over v thermal times 2. Okay, so that is called the drift velocity. The drift velocity. And now let's think about, that's for a single electron moving through, or charge carrier. If we have a solid with n molecules or atoms per unit volume and f free electrons per molecule, and each one has a charge q, each electron, that is, has a charge q and a mass m, then the current density is going to be equal to the number of molecules per volume times the number of electrons per molecule times the charge. So that all together has units of charge over volume times this drift velocity, which has units of length per time. So we have charge over volume, that is coulombs per meter cubed times meters per second, and that gives us amps per meter squared. So this is the current density. And then we can plug in for the average here, which is really the drift velocity. And so we just get, let's see, lambda over 2v thermal. Here's the NFQ. And then A becomes F, the average force, over M, using the equation F equals ma. And then finally, we know that F on a charge Q in an electric field E is equal to QE. So we can write F equals QE. So we get NF lambda Q squared over 2 mv thermal times E. So we find, according to this analysis, that J, the current density, is equal to a whole mess of constants combined, but proportional to the electric field. Okay, so that is a classical or semi-classical model. The real reasoning, or the accepted reasoning, is quantum mechanical, but this gives us the right idea for why Ohm's law fundamentally holds in a material. All right, let's talk about electromotive force. Electromotive force, or EMF, you probably associate with batteries, and that's a good association. So here's a sample little circuit with a battery lighting up a light bulb, and the circuit is complete. It has to be complete for the light bulb to light. So we can think about the force we know that there are charges flowing in this circuit. We can think about the force that each of these charges, the force per unit charge, so the force that each of these charges experiences. There's going to be a force that's supplied by the battery, which can be a chemical battery or a solar battery or a thermoelectric battery or even an electromagnetic battery known as a generator, which we'll talk about later. So the force would be equal to the force coming from the battery, Fs, plus whatever electric field is present. Because out here in the wire, we're no longer inside the battery, but something must be moving the charges through, and that something has to be the electric field. The electric field is also present inside of the source, but that is the battery. So the force per unit charge is the force of the source. Say that 10 times quickly: the force of the source, the force of the source, the force of the source. Yeah, you get the idea. Fs plus E. And then the EMF is going to be defined as the integral over the whole circuit of F dot dl. Okay, so the line integral of the force per unit charge with dl. And since we know that in an electrostatic field, which we're still studying here, the line integral of the electric field around a closed loop is 0. When we write this as Fs plus E, the integral of E dot dl doesn't contribute. So we can just write it as the integral of Fs dot dl. So let's take a look at the voltage and its relationship, the voltage between the terminals of the voltage difference, I should say, between the terminals of a battery and this EMF that we've defined. Well, first, the voltage, you remember, is defined as the integral minus the integral from A to B of E dot dl, where A would be one of these terminals and B would be the other. So for an ideal, what's called an ideal battery or an ideal EMF, the force current or charges can flow without any resistance within the battery. That is, for an ideal battery, there's no fluid resistance or electrical resistance or any kind of obstacles to the free movement of the charges within the battery. So if that's the case, then within the battery, the force F would have to be equal to 0, the force per charge F. But that means that this side has to be equal to 0, which implies that E is equal to minus Fs inside the battery, that is between terminal A and terminal B. So we can replace minus E with Fs, and we get that the voltage difference between the two terminals A and B is the integral of from A to B of the force of the battery source dot dl. But then we can extend that because we know that outside of the battery, there's no force from the source since we're outside the source. So we can extend that integral from just A to B to over the entire circuit, since the rest of the circuit doesn't contribute anything. Fs is 0 in the rest of the circuit. But this is what we just defined to be the EMF, or the electromotive force. Okay, so in a ideal battery with no resistance between the two terminals, V is equal to the voltage difference between the terminals is equal to what we've defined as the EMF. All right, what about in a real or non-ideal EMF or battery? Well, in that case, the force of the battery is going to have to be greater because it's going to have to drive the charges through a resistance. Okay, so the force of the battery is going to be greater than the electric field. And if the force of the battery here is greater than the electric field, then the EMF is going to be greater than the voltage difference between the terminals. And so the voltage difference between the terminals, V, becomes the EMF minus something, and it's usually written, it turns out to be proportional to the current that's passing through the battery. And so it's usually written as the EMF minus the current through the battery times what's called an internal resistance. Okay, so yeah, so we have an ideal battery with the voltage difference equal to the EMF, and a real battery with a voltage difference a little bit less than the EMF as we have defined it here. All right, what about motional EMF? Motional EMF comes, so in this diagram we have a circuit. It's a rectangular circuit of height h. It has a resistance R, and it's moving with velocity v to the right. And there's a magnetic field B here, which is pointing into the screen. So, and B only extends as far as this gray box. Okay, so what's going to happen here? Well, the charges, which are sitting here, are going to have a rightward velocity, and the magnetic field is into the screen. So if you set up your right-hand rule, you find that the charges in this part here experience an upward force. Okay, it's an induced magnetic force which drives them upward, and that is a form of EMF because it's exerting a force on charge between two terminals A and B, really. And that's motional EMF because it's coming from the motion the fact that the circuit is moving through a magnetic field, region of magnetic field. So the EMF would be the line integral of the force from the source, which here is the magnetic force dot dl, and that's going to be equal to, well, the magnetic force would be QVB. The force per charge would just be VB, where V is the velocity and B is the magnetic field. And then the length here is H, because it's this side which is experiencing the force between points A and B here. So the EMF here induced, the motional EMF, is VBH. The integration path here, notice, And then if we integrate around the rest here we V and B don't amount to any. The force is perpendicular to the circuit, so they don't do any work in forcing charges through the circuit. Same thing between A and D, and out here there's no magnetic field. So what we're really doing here in finding the EMF is integrating around the whole wire at one instant the force from the magnetic force, which is the effective battery here. The magnetic force is acting like a battery. But hold on here. We've got an EMF, and we've got current flowing. So that means this resistor is going to be heating up. So that means we've got to be doing work. We've got to be generating energy. But didn't we learn that magnetic force doesn't do mechanical work because it's always perpendicular to the velocity? So if you dot the magnetic force with the velocity, you always get zero. So the work should be zero. So what's going on here? There must be, the magnetic force can't be the one that's actually doing the mechanical work. And the answer to this is that as the current flows, the induced current flows upwards, it's going to experience another force because it's flowing upwards, and the magnetic field here is into the screen. And if you use your right-hand rule now to figure out which direction the force will be on it, it will be to the left. So we have a leftward force on those charges. And in order to keep the whole circuit moving at constant velocity, we must have a net force of zero. So we must have a pulling force to the right, this blue arrow, and per unit charge, it's going to be equal to U, which is the velocity of the charges in the vertical direction, times B. The full force would be QUB, but since it's force per charge, it's just UB. Okay, so then the work per unit charge. Okay, so it's actually this pulling force. Someone has to do this pulling because of this resistive force that we get from this back force from the magnetic field. So this pulling force, if we integrate it over to see how much work is done, it's going to, we have to realize that we integrate it over a different path here, because the charge itself is going to be moving simultaneously to the right because the whole frame is moving to the right, but also up because it's moving up in this branch of it. So it's moving up diagonally like this. So point B, when it reaches point B, B is going to be to the right of where it started. So it moves up at this angle. And if this angle down here is theta, then this length that it moves is actually h, the height here, divided by cosine theta. Okay, so if you set up a right triangle here with this angle as theta, you can verify that this hypotenuse is h over cosine theta. So the distance is h over cosine theta, and then because we're taking the dot product between the force to the right and that distance, we have to include the sine of theta. Excuse me. So we get UBH times the tangent of theta, and then this vertical velocity times the tangent of theta gives us the horizontal velocity V. So we get VBH, which is equal to what we calculated as the EMF. All right, so it turns out the work per unit charge is equal to the EMF, but it's not the magnetic force The magnetic force generates the EMF, but it's another force which is that does numerically equal work to the EMF, to the magnetic force, which does the work. Okay, so this is a little bit of a subtle point. You might want to, if that didn't completely sink in, you might want to listen to this slide one more time. Okay, finally, the magnetic flux approach to EMF. We're moving towards approaching Maxwell's equations. So we can define, we have already defined in our work on vector calculus, the flux as the integral of the vector field over a surface. So for this motional EMF doohickey here, we've got the area that has magnetic field has, or the region which has magnetic field going through it has a width of x, a height of h, and then the magnetic field is perpendicular. So B dot dA would just be BXH or BHX. Then we just notice that if we take the derivative of this flux, the magnetic flux through this region, which is the same as the magnetic flux through the whole circuit, since there's no magnetic field out here, we get d phi dt is equal to B times h, since B and h we assume are constant in time, times dx dt. Now, x changes in time because we have to imagine the whole circuit is moving to the right with velocity v. So the whole thing is sliding to the right. So dx dt is going to be negative because x will be getting smaller. And so it's equal to minus v, where we're taking v as a positive number, the positive speed of the system. But BHV is what we just calculated to be the EMF and also the work done per unit charge in the same circuit. Okay, so therefore we can say that the EMF can be found as minus the derivative of this magnetic flux with respect to time. All right. Now we've just shown this for here in this slide here. I've just shown this for a rectangular circuit, which has a fixed shape, but it turns out that it holds for a constant magnetic field. But it turns out it can be generalized, and you can check your textbook section to see the proof, where the magnetic field varies across the circuit or the loop, where the loop changes area and or orientation or position in time. So it turns out to be a very general relationship, even though we just showed it here for a very specific geometry. Okay, so this is a preview of Faraday's Law of Induction, which we'll be talking about next class. I did want to say one thing, and this is interesting. I actually just appreciated this in preparing this video here, is that this formula only works if we have right now a single loop of wire, which can continuously change its shape, orientation, or position, but not its connectivity, or what we might call its topology. So here's a counterexample to show that if the topology of the loop changes, this rule here doesn't work. So suppose we have a circuit set up like this, where we have magnetic field down here, and we have a junction, and the junction starts on at A. So the circuit would be the left side here, complete circuit. So there's a certain amount of magnetic flux. If we then flip this junction up to B, flip this arrow up to B, switching the junction, now all of a sudden the whole circuit would be the whole rectangle here. And so our magnetic flux would have increased. Our magnetic flux would have increased to include all this magnetic field. But when you do this experiment, you find that you don't get any current flowing through this ammeter. That is, there's no induced EMF and no induced electric field to drive current. Okay? And that's because the connectivity or the topology is changing. All right, so sometimes often we can use this expression here, d minus d phi dt, which will become Faraday's law next class. But sometimes to calculate the motional EMF, we have to be more careful, and we'll see an example of that. Not more careful, but take a more direct approach, and we'll see an example of that in the class problems. Okay, so we have studied in this class the Ohm's law and the behavior of materials. We've defined the EMF. We've seen the EMF is equal to the work done, but that the work is done in some cases by other forces besides the force associated with the EMF, particularly in a magnetic system. And we've seen that the magnetic flux relationship can be used to calculate the motional EMF. And next time we'll move on to Faraday's law. Thanks for your attention, and see you in class.